Hello, hello, welcome back. In our last lesson, we learned how to make those super cool Taylor polynomials. Today, we're going to talk about, well, how accurate are they? When we were doing divergence and convergence of series, we talked about the alternating series error bound. And remember, the error was all about the next term. It was all about the next term. And the error for a Taylor polynomial is similar to that. When we use Taylor polynomial approximations, it would be a good idea to know how accurate they are. Like this guy, we're pretty good up until here, but then, they kind of start to go their own ways. So this gap right here, we'd call that the error. If we know the error, we better understand what our exact value at a given point could be. So to find the approximate error, we'll start with that space there. And instead of calling it the error, we're going to call it the remainder. The exact value at a point would be the approximate value plus a remainder, which makes sense. So mathematically, that could look like this. F of x equals the Taylor polynomial approximation plus the remainder. Now we could solve for the remainder by rearranging this a little bit, and the remainder is the function minus the polynomial. We're interested in the absolute value of the remainder, the distance from the function to the polynomial. So the question is, what is the worst case scenario for the error? Here is our lovely Taylor polynomial. But you'll notice I've got the first part is the approximation, and then I've tacked on the remainder. Now, if we were working with a Taylor polynomial, the next term in line would be the n plus 1 derivative at c, and then x minus c to the n plus 1 and n plus 1 factorial. Now, this is where we start to dive into the unknown, right here, that n plus 1 derivative at c. So, our amazing mathematician, Lagrange, he tackled this, and he decided that the remainder would be defined as the maximum of the n plus 1 derivative at a times x minus c to the n plus 1 over n plus 1 factorial. So wait a second, where did that a come from? So our mystery a, what is it? Let's first of all define everything we have up here in this remainder definition. So n, that is the degree of our Taylor polynomial. C is the center. X is the value that we are attempting to approximate. Now, let's say that n plus 1 derivative is a strictly increasing derivative. That means we'd go from our center up to x. So x would give us a max error. If the n plus 1 derivative is strictly decreasing, if we go from c to x, well, this time c would give us the max error. If the n plus 1 derivative is unknown, well, then we say that a gives us the max error. Some textbooks, just so you know, use z instead of a. So the Lagrange error bound officially, let f of x be differentiable through the order of n plus 1. The error between the Taylor polynomial and f of x is bounded by this remainder, where a is some number between c and x. We also might shorten this to just say an m right there for max. Now, if the series is an alternating series, the error will be no greater than the absolute value of the first unused term. We learned that in a previous lesson. If a non-alternating series is approximated, then we're going to use Lagrange error. The keys to unlocking the Lagrange error mystery. First of all, we are finding a worst case scenario, not the actual error. It's still all about the next term. We'll generally find the value of this mystery fellow, the max n+1 derivative at A, in one of three ways. We'll be given a graph of the n+1 derivative, and we can use that to find a clear maximum. We'll know that if we're using a sine and cosine function, sine and cosine, the max of those is always 1. Sometimes they'll just give you the maximum value, either directly or indirectly. Here we go with example 1. The function f has derivatives of all orders for all real values of x. Let p sub n of x, that's our polynomial, represent the nth degree Taylor polynomial for f at x equals 1. Show that the distance between f of 1/2 and the third degree polynomial at 1/2 is less than 1/12. We have a third degree Taylor polynomial, which means our error is going to be living in the fourth derivative. Now we want to approximate at 1/2, so we can go ahead and plug in a 1/2 for x, and we also know that we're centered at 1. So we can clean this up a little bit. 1/2 minus 1 to the fourth, let's just go over here for a sec, is 1/16. So hold that there. Now, what do we do with f to the fourth of c? Well, look over here. They've given us the graph of the fourth derivative, even the absolute value of it. So if we look at the graph, what's the maximum? Well, it's hanging out about here, but I don't know, like what value is that? Is it 27, 28? Who knows? But we know it's less than 30. So we're going to use 30 for that. And then times our 1/16 divided by 4 factorial, which is 24. And we get 5/64. Is 5/64 less than 1/12? Yeah, it is. Example 2. The fourth degree Maclaurin polynomial for cosine x is given by that guy right there. If this polynomial is used to approximate cosine of 0.2, what is the Lagrange error bound? All right, we've got a fourth degree Taylor polynomial, and at point 2, we would get an approximation of 0.980067. Okay. How far off could that be? Well, if we're in a fourth degree Taylor polynomial, then we're going to live in the 4 plus 1, or the fifth derivative. Our power will be 4 plus 1, and our factorial will be 4 plus 1. So what do we do about that max derivative value? Well, if we look at the various derivatives of cosine, it's cosine x, negative sine, negative cosine, sine, cosine, negative sine. It stays within the sine and cosine family. The fifth derivative would be negative sine of something, but sine and cosine, they never go above 1. So we'll just put in a 1 for that. That's very safe. And then let's go back up to the top, because I didn't talk about that. We're estimating at 0.2, and we're centered at 0. So we've got 0.2 to the fifth that we've brought down, all over 5 factorial, and then we can put that into our calculator. And wow, look at that, is a small, small number. So this polynomial here is going to be a very, very close approximation of cosine of 0.2. That's super cool. Example 3. Let f of x be a function that's continuous and differentiable at all real numbers. Assume that f of 4 is 5, f prime of 4 is 7, f double prime of 4 is 18, f triple prime of 4 is 24, and also, look at what we have here. The fourth derivative of 4 at x is always going to be less than or equal to 45 for all x in this little tiny interval from 4 to 4.2. So first, we'll find a third order Taylor polynomial about x equals 4. So if we set up our general Taylor polynomial about x equals 4, and now we just get to plug in all the information they gave us. So f of 4 equals 5, f prime of 4 equals 7, and so on. If we plug in 4.2 to that, our polynomial gives us an answer of 6.792. Part B, find the maximum possible error for f of 4.2. Well, that's going to live in the next term. Now, they already told us that the fourth derivative, the value of the fourth derivative, is always going to be less than or equal to 45. So that's our max. And then we just go with x minus 4 to the fourth over 4 factorial, plug in 4.2 to that, and we have a possible error, a maximum error of 0.003. So part C says, find an interval AB such that the actual value of f of 4.2 is between them. Well, what we're going to do is take our polynomial approximation and we'll add the error and subtract the error. Oh, I went the other way. So that gives us a possible range of the actual value of f of 4.2. Example 4. Selected values of f and its first four derivatives are indicated in the table below. The function f and its derivatives are positive and increasing on the interval 0.6 and 1. Use the Lagrange error bound to find an upper bound on the error of the approximation f of 0.6 by a degree 3 Taylor polynomial for f about x equals 1. There's just so many words, so many words. If we have a third degree Taylor polynomial, then our error is going to live in the fourth degree term. So what we don't know is the maximum of the derivative at a. We are centered about 1 and we're approximating 0.6, and that's to the power of 4 over 4 factorial. So what do we do about that max of the fourth derivative at a? Well, they gave us in the table here the answer to that part, 119. Plug all that into your calculator, and there we have it, 0.127. Example 5. What is the smallest order Taylor polynomial centered at x equals 1, which will approximate e to the x minus 1 between 0 and 3 with an error less than 1? Let's start by working through our derivatives. So e to the x minus 1, it's just always going to have a derivative of e to the x minus 1. Now at 1, that's always going to be e to the 0 then, so that'll always be 1. But in general, mystery derivative at a, we could name that e to the a minus 1. So if we put our polynomial together, the remainder here is going to live in the n plus 1 term, and that n plus 1 term needs to be less than 1. Well, I don't know which term that's going to be, so I'm just going to write in here max e to the x minus 1. And then I've got x minus 1 to the n plus 1 all over n plus 1 factorial. Now, what do we do about that? Well, let's look at here. We're going on the interval between 0 and 3. So a has to be somewhere in between there. So if we plug in 0, e to the 0 minus 1 is 1 over e. If we plug in 3, e to the 3 minus 1 is e squared. E squared is bigger, so that's going to be the maximum. Now, to figure out the smallest order Taylor polynomial, we need to know what n is. So your calculator comes in really handy for here. If you plug that into the equation editor, pull up a table, I can make it bigger for you. Right here, the remainder is less than 1. So we'll need a fifth order Taylor polynomial in order for our error bound to be less than 1. And that is the end of that Lagrange error bound. Sometimes it takes a while to get the hang of Lagrange error bound, but I know you can do it. Okie dokie, see you next time.